So we should have already done those problems on page 409. Don't just do this and have me do them for you, right? Go through those and then have me run through them like we normally do with homework type stuff. So number one, what is the relationship between pitch and frequency? The greater the frequency, the higher the pitch. Pitch is our body's way of interpreting frequency for sound, right? It's to compare that, right? Amplitude would be like the loudness, right? Or the volume of it, right? Two, dolphin's echolocation is similar to ultrasound. Reflected sound waves allow the dolphin to form an image of an object that reflected the waves. Dolphins can produce sounds of frequency ranging from 0.25 kilohertz to 2200 hertz, but only those at the upper end of the spectrum are used in echolocation. Explain why higher frequency works better. Well, that's just definition, right? It's like a high def TV. The more pixels you have, the sharper your image is. So the higher your frequency, the closer together your waves are, the sharper an image you're going to get. If you use really low frequencies, then you're going to just get there's something over there, but I don't know what it is, right? So you want them close together so you have more definition in the picture kind of thing, right? Sound pulses emitted by a dolphin travel through the ocean at 1,450 meters per second. In air, those pulses would go at 340. How can you account for the difference in speed? The difference in speed would be based on the densities of those things, right? So the further the molecules have to move, so the less dense that stuff is, right? So then that molecule has to move far before it bumps into it. The wave propagates through it slower. Remember, the wave is not the material moving, it's the wave moving through that material, right? But the further that material has to move to allow that wave to move through it, the slower it's going to propagate through there. So things that are more dense propagate that speed much quicker, right? Could a portion of the innermost wave front shown in 1.7 approximate a plane wave? So a plane wave is just like a sine curve wave, right? Like a wave like this kind of thing. So as you get far out from a circular wave function like this, out here, that's pretty close to this. But in here, really that's not right there because it's curved too much. So not really, but I don't know that's just an interpreting graph kind of thing, right? In a diagram of the Doppler effect in a ripple tank, right? So a ripple tank is a tank that just makes ripples for you. And if you put something down in it, you can then perceive that and that kind of stuff. In which direction is the source of the ripple waves moving, right? So figure 1.8 definitely looks like this, where you've got one side that is a lot closer and one side that's more spread out. I'm bad at drawing circles. Right, but it's like closer on one side than on the other. I'm bad at drawing circles. I shouldn't have bothered to try and draw it. But they're all bunched up on the right side of the page. So you would have to say it's probably moving to the right. Right. Number 6, if the source of waves is stationary, which direction must the ripple tank be moved? So let's say you're just bobbing your finger up and down like this in the ripple tank, and the ripple tank then has to be moving to the left. Right? Because like anything else, the motion of sound is relative. Now my glasses look crooked on there. I know my nose is crooked, but that's weird. Okay, so I can see myself, and that's distracting to me. So anyway, motion's relative. Just like it doesn't really matter if you're moving towards the car or the car is moving towards you. It's just the distance between you that's changing. Same thing with the Doppler effect. Doesn't matter if you're moving or the object is moving. It's how you're moving together that makes the difference in what you perceive, right? So it would be moving to the left, or the object is moving to the right, either of those kinds of things, right? As a dolphin swims towards a fish, the dolphin sends out sound waves to determine the direction the fish is moving. If the frequency of the reflected waves is higher than that of emitted, is the dolphin catching up or falling behind? So here you kind of got to picture what's going on. So if I'm gaining on them, then those should be getting closer and closer and closer together, right? But they said the frequency of reflected waves is higher than that of the emitted waves. Oh, okay, yeah. So the frequency is higher, so that means we're catching up to it. If they were lower, that means you're falling further and further behind. That's basically how cops' radar guns work. They're sitting stationary, and they shoot their radar gun at you. It hits you, and then it comes back, and then it goes back and hits you again. And there's a little time difference between those. And then it says, well, what was the difference in how long those took to get there, right? And so then they can know if you're speeding or not speeding or whatever, right? Okay. That does it for those. Hopefully that helps. Go ahead and take the little quiz over the homework problems and Doppler effect.